Let me continue my discussion on quantum confinement, and then I'll go on to quantum well lasers as such. I was in the midst of a derivation trying to find out the electron wave functions when we have a finite well of height V0. This is the well, these are the two barriers, and the well width is, say, LZ. We can think of waves propagating in the various regions given by DC in the barrier and A and B in the well. We had seen that we had to solve Schrödinger's equation minus h cross squared by twice mi d2 fz by dz squared plus vi plus vki fz is equal to ei fz, where fz is the envelope function and vki is h squared kx squared over twice mi. This is the kinetic energy in the x and y direction. So at the beginning we had said that, okay, let's put this equal to 0 and consider this is for bound states. Okay, in the well we can say that we can add this term later on to the energies. So in the well, VW is equal to 0, and so we had chosen solutions of this type: FZW, A exponential. A is the amplitude of wave traveling in the plus z direction, plus B exponential minus kzz, where kz squared is twice mw over h squared ec. In the barrier, VB is equal to, potential in the barrier is equal to V0, and then we have VZB plus on the right barrier. We have C1 exponential alpha ZZ plus, in general we have two terms, C2 exponential minus alpha ZZ. Okay. Notice these are exponential waves increasing and decreasing with Z. And similarly, in the left-hand side barrier, we have FZB minus is equal to D1 exponential alpha ZZ plus D2 exponential minus alpha ZZ. These will be simplified. What is alpha Z? Here, alpha Z squared, like kz squared, is equal to twice mb, mass of the electron in the barrier, which is different from the mass in the well, by h squared, v0 minus ec. Okay. So these are important expressions that we'll use later. So to solve the problem with wave function, determining the wave function, we have to find out A, B, C, the 6 unknowns, 1, 2, A, B, C1, C2, D1, D2. Okay, but we can simplify from the physical conditions because we know that the envelope functions must go to 0 at z going to either plus or minus infinity. Okay? So if you look at this, then obviously at plus z equal to plus infinity, this blows up. Then obviously this must be equal to 0. And at d equal to minus infinity, this blows up. Okay, because we are talking about this. Here we have fzb plus. Okay, and here we have the function fzb minus. Okay, left-hand barrier, right-hand barrier. So in order to have realistic boundary conditions, then this d2 must be also equal to 0, okay, because of this requirement. Therefore, C1 equal to d2 is equal to 0. So two of them have gone. And further boundary conditions are that we have to match fz, continuity of the wave functions and its derivative, and 1 by mi df z dz at two interfaces. This is like the usual WKB type of problem. So from the symmetry of the wells, we find that B is equal to plus minus A and D must be equal to plus minus C. Okay. So here we have A is equal to plus minus B, and well, this C2 just becomes C and D1 becomes D, so these must be plus minus. So depending upon, suppose we have B is equal to A, okay, and D is equal to C. These are called even solutions. And equating, substituting in the main equation and solving, we get the condition in this case that tan kz Lz by 2 is equal to mw by mb alpha z by kz. Okay. Where what are these alphas and k's? The alphas and k's, k is known in terms of this 2mw ec, and alpha is known in terms of V0 minus ec. Okay. This is mass in the well, this is the mass in the barrier involved. And notice that because these masses are different, we have this term mw by mb. Okay. And for odd solutions, the case B is equal to minus A and D is equal to minus C. Okay, these are called it's even or odd symmetry, that is all that is meant. Kz Lz by 2, its cot function, okay, is equal to minus mw by mb alpha z by kz. Okay. So these are the equations that determine the nature of the energies, and they can only be, these can only be satisfied by discrete energies. Discrete sets of energies. Say ECN. So to illustrate this, suppose we have potential well, finite potential well, okay. So we're going to all the trouble to just to see what happens in the case of finite potential well. For n is equal to 1, the wave function is obviously of this type, peaking in the well. For n is equal to 2, this is the energy, okay, and the nature of the wave function is anti-symmetric. This is symmetric. So similarly, we can draw the nature of the wave for this amplitude of the wave functions. Notice here that MW is not equal. This is not the case of a free electron. MW is not equal to MB usually, and M star can vary spatially. Okay, now that is in the well. This is in the Z direction. Okay, but what happens to the case when V is not? We have taken VKI. Okay, VKI is equal to h squared kx squared kxy squared by twice mi. Suppose this is not equal to 0. Okay, so that means there is some energy. So the total energy is a function of xy. Here, obviously, there's a parabolic relation. Okay, so this is in the xy direction. This is energy. So we'll have a set of parabolas for n equal to 1, n equal to 2. Okay. So in this case, we have the full energy relation EC function of kxy is Cn0. This is the bound state energy plus h squared kxy squared over twice m effective. And now what is this m effective? It turns out that this 1 by m effective is nothing but gamma mw plus 1 minus gamma mw. Sorry, this must be mb. mb. So what is this gamma? Gamma is a confinement factor. So again, it's somewhat like electron in a waveguide. Okay, when electromagnetic waves propagate, we have a confinement factor. Confinement factor is the amount of the energy of the electromagnetic wave in the central core. Okay, and 1 minus gamma is the part outside the core. So here, the effective mass. This is the part of the electron wave function which is in the well, and this is the part which is outside the well. So what is this confinement factor? Exact, almost analogy with fiber optic propagation. We have a confinement factor gamma. Gamma is equal to the amount of the wave function which is within the well, Lz over minus Lz by 2 to plus Lz by 2 into this envelope function amplitude fzn0 squared dz over the whole thing, but going from minus infinity to plus infinity. Okay. So this is a confinement factor, and it is apparent from let's see which one. Yeah. Okay. Obviously, you can see that the confinement factor, that this is the part which is in the well, okay, where the effective mass is mw. Okay, and here this is the part which is outside the well, this is mb. And of course, we know that why is confinement occurring? Because this is say gallium arsenide. This is aluminium gallium arsenide. Okay, so obviously the effective masses are going to be different in the two regions. Okay, using these, one can actually calculate the bound state energies finite well. Okay, this is aluminium indium arsenide, gallium indium arsenide, lattice matched on indium phosphide substrate. Okay, this is the bound energies going up to about, say, 0.5, and this is LZ in angstroms. Okay, it has a lot of similarities with the infinite well problem. Obviously, as LZ decreases, the bound state energy will go up. So typically the value, okay, so this is 200, this is 100. Okay, what will be the nature of the variation? It will be at 50, it is about here. Okay, so okay, this is E1, and similarly we'll have E2, E3, E4, okay. So what do we see? That obviously as LZ decreases, this energy E1, E2, okay, as this decreases, the energy increases. Okay, and obviously all of them, E2 increase, E3 increase. What happens if you go to, say, this is 50 angstroms. Suppose you go to something like 30 angstroms. Okay, in this system, if LZ is less than 30 angstroms, okay, say somewhere here, okay, okay, there is only one bound state, because delta EC in this case we are assuming is 0.5 eV. Okay, the finite well width is 0.5 eV. Okay, so if LZ is less than 30 angstrom, there is only one bound state. In the well, the rest of it, what happens is, okay, if you squeeze it like that, there is one bound state somewhere here, E1, and the rest are above. Okay. So this has implications in the sense, if you want to have excitations between E1 and E2, obviously in this case, the excitation will take the electron out of the bound state, out of the well. So you are not going to get excitations up to higher states here. Okay. Similar calculations can be done for holes, but I've just mentioned that for holes, here we have in the conduction band S-type wave functions. Okay, so there's spherical symmetry. In the case of holes, it's more complex. You have P-type wave functions, okay, and so the effects are more complex. Okay, I can illustrate it diagrammatically, that we have E in MEV. The other complication is that we have heavy holes and light holes. Okay, so in the bulk we have, say, something like this. Heavy hole 1, light hole 0, heavy hole. Okay, in the quantum well, when we have mixing between the heavy hole and light hole wave functions. Okay, then we get a wave. This is a function of ky. Okay, this is a function of ky. Then we get variations of this type. It's quite distinct, and this is with mixing between H and L, heavy and light holes, and this is bulk. Okay, I won't go into more rigorous calculation. This is just to show how these calculations are done, and as I mentioned last time, if you want to compare with experiment, we can make wells of different widths going from 50 or even 20 or 30 to 200 angstroms LZ. Okay, this is interesting. That, and as you confine it, you can go up to, this is 1100 MeV. This is the well-known in-gas indium phosphide lattice match system. So we are not involving strain or anything here, just for calculations, and we find that theoretically, if we take delta EC is 0.5 EV, okay, this is 0.5 EV, we get one type of, okay, we get one type of variation, something like this. And if delta EC is 0.22 EV, which is more realistic for this system, 0.22 EV, then you get a variation of this type. So as the, so if the barrier height is higher, then you get obviously more. For a particular value of LZ, you will have higher confinement, higher energy. Okay? And experimentally, what does it compare with? Experimentally, this is Razagi's data. You have 1 point here, but the other points are way off. There's about 50 angstroms well, okay. So experimentally, if at all, the agreement is much better with delta EC is 0.22. It is of this order and not definitely 0.5 EV. Okay, is that clear? That in somebody asked me yesterday that what are these delta ECs, and it is system dependent. Okay, it depends upon the heterojunction band diagram. If you have gas-algas system, these are the two most well-known systems. Okay, then you draw the diagram like this. Okay. Delta EC by delta EG is typically, earlier they used to think it was, now it's about 0.6, and delta EV, delta EG is obviously 0.4. Okay. So depending on what is the composition. But if you take the in-gas indium phosphide system, again lattice matched, then delta EC, delta EG is of the order of, you can take about something like 0.35, or you can say it's the opposite. Delta EV, delta EG is about 0.6. This is really, it could be 0.35 to 0.4. This is 0.6 to 0.65. Okay, 1/3, 2/3 type of. So that depends. That determines the wells in the finite quantum well. Okay, let me push on a little faster. So it turns out that if you take quantum wells of where the density of states is given by a step-like function, okay, and the quantum well width is LZ, then if you calculate the gain using the usual techniques of calculating the transition matrix elements, etc., then you find that, say this is current J, J norm, the volume current amperes per centimeter cubed, versus this is gain. For bulk, you have the gain takes off. If this is losses, okay, then where the gain cuts the losses, okay, that is the minimum sort of transparency current. And for quantum well, the basic advantage is that you have much sharper linear variation, and this intersection is at much lower currents. Okay, so that is so G max is given by some beta J norm minus J transparency. So that is the basic advantage of quantum wells. Now, if you go to the differential gain, again as a function of well width. Okay. So what do you find? That as the well width, this is the bulk, differential gain is dGn dN. N is the carrier concentration. As you're pushing in more carriers, quantum well differential gain is much more than in the case of bulk. Okay, so that again is an advantage of quantum wells. And if you look at the actual transition energies, it's obvious that you have a selection rule. Say this is n is equal to 1, and this is the first one is n is equal to 1. Okay, so the transitions are the selection rule is delta n is equal to 1. Delta n is equal to 0. Okay, so you will have so that is the principal transition that is involved. And in order to verify that, what does one do? One makes wells with different widths. This is what we've done by MOVP also, that if you grow, these are the barrier layers, the shaded are the barrier layers, and these are the wells, 90, 60, 50, 40, 30. This is gas-al-gas structure. Okay, so in one growth run, you can grow these wells, and if you probe it by laser light, you will get from the 30 angstrom barrier, okay, here you will get the emission at 6,800 angstroms. Okay, from the 90 angstrom barrier, here you will get emission at 7,840. So this energy immediately tells you what is the well width. And as expected, as you have a narrower well, this wavelength goes to shorter values. And so with the same material, just by varying the well width, you can get devices working at different wavelengths. Okay, then the question comes out that, okay, do we always gain by having, what is the number of single quantum well versus multi-quantum well? How many wells do we have? Okay, so it turns out that although single quantum wells have high differential gain, but a single quantum well is at low values of n. A single quantum well can only contain so many number of electrons, whereas multi-quantum wells you can have a high delta G, delta n at high values of n, and that means at high values of J, injection current. So does that mean you keep on increasing the number of wells? No, the problem is that one of fabrication. Okay, this is basic physics. Okay, the other reason is, what is the optical confinement factor? It's fine, you're getting a recombination, but how much of the light is actually, how much of the electrons are actually in the, and it turns out that for the lasing, for the fundamental mode, this optical confinement factor gamma is something like d squared over 2 plus d squared, where D is equal to K0 mu A squared minus mu C squared to the power half. Okay. Now we are talking about optics. Okay. So the optical confinement factor is given by where K0 is 2 pi by lambda. Okay. And mu A is a refractive index. These are the refractive indices in the active and the cladding region. So this is larger than that. Okay. Refractive region. This is refractive indices in the active and the cladding region. And as you can quite well understand that if you have a single quantum well, okay, say 50 angstroms, what is the light? How much of the light is going to be confined in this? This is going to be extremely small. And say for D less than 300 angstroms, this gamma has there's a simple relation. This is okay. This is from this you can see it's just half D squared. Okay, a half. And so gamma becomes something of the order of, if you put in the value, something like of the order of 0.01. Okay, so this is another disadvantage of single quantum wells. So you will go to more wells. But then the third reason comes, what are the fabrication problems? How many wells can you make exactly equal and with the same geometry? So it turns out that for multi-quantum wells, most of the multi-quantum well devices have about, one can actually do this mathematically and calculate how the gain varies, how the differential gain varies, J varies. The number of wells is typically of the order of 4 to 6. Okay. The same problem of optical confinement is tackled in different ways. This is the typical multi-quantum well structure, right? Can you see this? Okay. So here you have not the energies, but the refractive indices. So the wells, these are the wells. Okay. Well, these are the wells and these are the barriers, because the refractive index in the well is high. Okay. So there are 3 wells. Okay. So obviously there will be some confinement here, but because these LZs are very small, the optical confinement is going to be much less than in the case of a double heterojunction laser. How can you improve that? Well, you can have a modified multi-quantum well, okay, in which you have, this is the cladding, and then you can have steps. Typically, if this is indium phosphide, okay, so this could be indium phosphide, okay, then this could be indium gallium arsenide phosphide of a particular composition, and then this could be indium gallium arsenide phosphide with a higher refractive index. And remember, refractive indexes and band gaps are inversely related. Okay, so if you go to a lower band gap material, okay, refractive index will be. So that is one possibility. The other possibility is things like this, which are.
So we need a higher refractive index
in the well. Yeah, obviously. Okay. And that is the way it is. Gallium arsenide has a higher refractive index than AlGas. Okay. So here.
Sir, here what is the difference between first and second? Same.
No, here. Yeah, you have this dimension can be of the order of 0.1, 0.2 microns. Okay. And these, remember these, if you have 4 wells, 4 barriers, they could be, say, 50 angstroms. Okay, 50, 150. So 200. These are only of the order of a few hundred angstroms. Okay, and this could be of the order of 0.1 micron. Okay, so you're getting more confinement. An even better geometry for confinement. This is a single quantum well, okay, graded refractive index, this parabolic. So this is almost learning from optical fibers, where you can have different types of refractive indices, and this is done by doping aluminium, just controlling the aluminium concentration. Okay, so this graded refractive index (GRIN), separate confinement heterostructures. So separate confinement, the electrons are confined here, okay, and the light is confined here. Okay, separate confinement quantum well heterostructure device. Okay, and here it's you have, instead of a parabolic, you can have a linear profile. Okay. So these are the basic types of structures that go into quantum wells, and going to actual achievements in final devices. We know that, say, for example, looking at JTH, amperes per centimeter squared, this is 1960 to 1990. The first homostructure lasers had 10 to the power 4 amperes per centimeter squared, somewhere here. Okay, and now we are down to quantum wells having threshold currents of the order of quantum wells somewhere here. And quantum wires and quantum dots have come down even further. Okay. This is typically of the order of, say 100 amps per centimeter squared, and here we've got down to about 10 amps per centimeter squared. So overall, not only do quantum well lasers have lower JTH, they have lower DJTH DT, which is very good for systems. We know that, say, for example, JTH is equal to J0 exponential T by T0. Okay, so for a particular wavelength, if T0 is, say, 60 for double heterostructure lasers at 1.5 micron, okay, T0 would be something of the order of about 90 for a quantum well laser. And we know that these values, they depend upon the wavelength of operation. Why? Because at a longer wavelength, the band gap is less, so the temperature dependence is more. Okay, so the temperature dependence is less. Also, we can have single mode operation. Okay. In this case, what is the gain relation? Gain relation is confinement factor gamma into GTH, because part of the light is in the active layer, so alpha A into gamma plus into the cladding layer, okay, 1 minus gamma, okay, plus 1 by L long. So the old relation is divided up into, this is the absorption in the active region, this is the absorption in the cladding region. Okay, so this is the general relation, and this is due to the mirrors. And another, for systems applications, another advantage that I could make is that there is lower chirp. Okay. that is the variation of frequency with current, injection current, or with temperature. You want a laser to work at this, no matter at low level or high level, the frequency should not shift. Okay, so suppose you're looking at the spectrum, the laser at low intensity. Suppose this is the laser line at low currents. At high currents, it should not. This is the intensity. This is say frequency. Okay, there should not be any shift, because if you have multiple channels, okay, you will get overlap. So it turns out that this is very important in communications applications. Chirp is measured in angstroms. How many angstroms shift will you get? This is say 1 angstrom. Okay, and this is a function of I, current. There will be a small amount of chirp, but in the case of a bulk double heterojunction laser, the chirp line will go something like this. Okay, double heterostructure laser. Whereas for a multi-quantum well laser, okay, the chirp may be much less. Okay, so this is again another big advantage of multi-quantum well lasers over the usual double heterostructure lasers. Okay, I think I'll stop there. And in the next class, I'll go on to a discussion of modulators.